Hi everyone, my name is Nour Fahmy, and I'm the Math and Foundation stream owner here at ACE. ACE, if you've never heard of us, is a community of machine learning practitioners and researchers who have gathered around topics in AI research, engineering, and products. We host free live sessions like this 3 to 5 times a week and produce premium content in various subject areas. To see more, visit AI.SCIENCE and log in to access slides from this and other sessions and many more. Also, make sure you subscribe to our YouTube channel, ML Papers Explained, to get notified about all the live sessions and other free content we publish. We currently have more than 30 different streams that are focused on various ML topics, and this session is in Math Foundations. Hope you enjoyed and come back. Today we have Miles Cranmer, who is a graduate student at Princeton, studying the intersection between astrophysics and machine learning.
Thanks. Yeah, so today I'm going to tell you about Bayesian neural networks in general, and then a specific problem to model chaotic systems with BNN. So this is work with a group of people in some in astrophysics, some in deep learning. So if you remember nothing else from this talk, I want you to remember these two pieces of intuition. So the first is, if you're trying to model a chaotic system, some system where you're kind of uncertain about the I guess like how you perturb the initial state is going to affect the final state. So if you're working with a chaotic system, you should use Bayesian neural networks. I'll tell you what this is. So the second point is, when you are designing a neural network, it's really important, and I've experienced this so many times for different projects. It's really important to use handcrafted models for some specific problem. Use the same structure to influence the architecture of your model. So like a simple example is like a convolutional neural network is kind of it's kind of related to a handcrafted model for computer vision. So it's kind of like influenced from the handcrafted model. So this is a point I'm going to emphasize. So let's talk about Bayesian neural networks first. So if I guess the best way to introduce this is, if I have a neural network and I'm trying to learn this relationship, so year on the x-axis and then the number of airline passengers on the y-axis. This is from one of Andrew Gordon Wilson's papers. If I'm trying to model this relationship with neural networks, how do I fit it? Because a key detail is that there's a spread, right? There's this big spread in the data. So if I try to fit this with a neural network, maybe it's going to try to like overfit through every single data point, or it's just going to fit the mean line. But what if I really want to understand this actual spread of the data? So to do this, what you usually do is you predict, you don't predict the airline passengers, you predict a distribution over the number of airline passengers. So you actually predict the mean and the spread of the output. So in this example, you could maybe predict the mean airline passengers and then the spread in the airline passengers. So this is a common way of modeling uncertainty with neural networks. It's this specific type of uncertainty is called aleatoric uncertainty. So this is like the natural intrinsic spread of data. So another type of uncertainty is due to the fact that neural networks are very redundant models. So there's many different parameter choices, and you'll get the exact same model with a different parameter value in the minima, but it's the same exact model. So they're very redundant, and I guess like how do you know which values to choose? Because there's a lot of redundant models that give you the exact same loss. So the way you do this when dealing with uncertainty is you try to model all of the different parameter values that give you the same prediction, and you average over these models. So this model gives you the same loss, and this model gives you the same loss. You actually take those models, you predict with both of them, and then you average over them. And you can look at the spread of those models too. So this is like this is a way to model the epistemic uncertainty of their model. So this is like the model-based kind of extrapolation uncertainty. So like if I try to extrapolate I don't really know where it's going to go. So this is called the epistemic uncertainty. So this is what a Bayesian neural network is. It deals with this aleatoric uncertainty, so the data spread, and then also the uncertainty due to model extrapolation. So in a regular neural network, maybe for a problem where you're trying to predict a value, so you're trying to predict a value y, the Bayesian neural network equivalent, you now predict y and sigma. So sigma is like the Gaussian spread in y. Then the next thing is you take your neural network, which has all these weights. So like this weight is 0.5, 0.1. And now instead of dealing with single numbers, you deal with a distribution of these numbers. So you can think about instead of 0.5, this is like a distribution over potential values for that weight in your neural network. So this is the second step to transition to a Bayesian neural network. The third step is you train it with the negative log likelihood. So this is if you fit this regular neural network with mean squared error loss. In a Bayesian neural network, you train with this loss. So it's the squared error divided by sigma squared plus log of sigma. So this is it's 2 times the negative log likelihood of a Gaussian. So you're optimizing the log likelihood. So it's like you're training this probabilistic model now. So the simplest type of Bayesian neural network is actually dropout. So when you train with dropout, you randomly turn on and off different nodes in your neural network. So if this is my full neural network, I maybe turn off these nodes randomly, and that's my dropout. So the trick that Nour and Gal realized is that you could dropout is actually it's actually a type of Bayesian neural network. So a dropout is you're actually modeling a distribution over parameter values. The trick is that your parameter is either the normal parameter of the neural network or it's 0. That's a distribution over values. It's only 2 numbers, but that is a distribution over parameter values. So that is actually a type of you're modeling a distribution over parameters in your neural network. So what you can do with that is you can actually train a Bayesian neural network. So if I'm fitting these points y as a function of x, this is what's called a Monte Carlo dropout network. And you can see it actually has this spread in the predictions. So this is a Bayesian neural network. You get this uncertainty in the prediction. So this is a really nice approach because it's just you train with dropout and then you just leave dropout on after you're done training, and it like automatically becomes a Bayesian neural network. So the only trick is you have to train with this loss instead of this one. So a more sophisticated approach is it has to do with something called stochastic weight averaging. So when you're training a neural network with like stochastic gradient descent, you're going to approach a minima, and then you're kind of going to move around in the minima if you keep the learning rate fixed. So you can see this is like the trajectory of the optimizer. It's going to move around in this minima. Now, what some people realize is that this kind of random walk in parameter space when you're at the minima is actually it's kind of equivalent to fitting a parameter distribution with Bayesian methods. So when you're randomly walking around the space, it's kind of like you're randomly picking new parameter values. So it's a really powerful idea. But basically, the first paper, so stochastic weight averaging, they basically realized that if you track the optimizer when it moves around the minima, and you just average the weights, over the trajectory in this minima, it will generally find a better optima than if you just trained with stochastic gradient descent. So it's like you average over this final steps, and you usually just get a better model. So it's a really cool idea. The second paper by this group is called Stochastic Weight Averaging Gaussian, or SWAG. And what they do here, instead of just fitting the mean of the path of your optimizer, so you're randomly kind of moving around space when you're optimizing the parameters, instead of just fitting the mean, what they also do is they fit an entire Gaussian. So a Gaussian is kind of like this blob in your parameter space. So what they do is they track the optimizer as it moves around in the space, and you literally just fit a Gaussian to the minima. So it kind of looks like a Gaussian. So what you do, you literally just fit a Gaussian to the space. And so this is a really kind of like, it's so simple, it's genius. It's this really nice idea that makes an equivalency between Monte Carlo sampling and stochastic gradient descent. So to be honest, like it requires even less modifications than Monte Carlo dropout, because you don't even need dropout here. You literally just record the optimizer, fit a Gaussian to your parameter space, and that's like so like maybe this is one weight, this is another weight, and you literally just fit a distribution in this space. And that's like a distribution over your weights. So the follow-up I did to this, which was proposed last year from Andrew Gordon Wilson's group, is instead of just fitting one Gaussian, why don't you fit multiple Gaussians to your parameter space? So like I said earlier, neural networks are very degenerate models. So there's a lot of different choices of parameters that give you the exact same model. So what they do in this work is say, why don't we fit, instead of one Gaussian, fit many Gaussians in parameter space? So like if this is one parameter, this is another parameter, you're now fitting multiple Gaussians in this parameter space. And this is it's a distribution over the parameters of your neural network. So like if this is my, maybe this is like my loss surface. So I want to find the minima, like the lowest point. You can see that I think the green circles are MultiSWAG. And you kind of have different points in parameter space. And what you would do during inference is you randomly pick one of those dots and evaluate the model for that choice of weights. And then you pick another random dot in your parameter space, evaluate the model, and you keep repeating this. And what happens is you fill out a distribution over the predictions. And the average prediction is actually going to be, it's going to be like a very, I found it's much more accurate than just a normal prediction from a neural net. And the other cool thing is you get error bars on your neural network, which is like, not only is that, like, it's kind of cool to have uncertainty from your neural network where it predicts its own error bars, but that's also really important for a lot of applications like physics. We kind of want to know how confident is it about these parameters. Maybe like if you're doing like self-driving cars, you kind of want to know the uncertainty of your car, like if it doesn't really know if this is like a billboard or a truck, like it should tell you that it doesn't know. So these Bayesian neural networks are really powerful, and they're also really high performance. They give you these error bars on your network. So, okay, so the next thing I want to talk about is deep learning for simulations. So in this is like a double pendulum, and maybe my double pendulum is here one step, and then it moves here, and I want to predict what's the next step. So this is like the simplest example, and basically what I want to do is feed in the angles over time, and I predict the next angle. So this is like the simplest example where I want to use a neural network to predict the next step of my simulation. And so in industry and academia together, there's a lot of different problems where the bottleneck, the really expensive part, is just simulating things. So real world simulations are very complex and they have high computational expense. So what deep learning can do is, if you train a deep learning model to kind of run your simulation for you, it can often learn more efficient ways of doing so. So like a recent really nice example is AlphaFold from DeepMind. They train this neural network to kind of find a better way of doing protein folding. And there's many examples in like fluid dynamics, and they can like speed up orders of magnitude your simulation. So you basically, you take your neural network and you try to predict many time steps in advance. So this turns into a prediction problem. Your input data is like your initial state of the simulation. The final data, which you want to predict, is like the final state of your simulation. And it'll basically learn to do this in an efficient way. So a really nice recent example from Dima at Google, they train this model to, so they have this fluid simulator, and it models turbulence in a fluid. And what they do is they take a simulator, they lower the resolution of the simulator so it's faster, and then they take the neural network and they basically ask, okay, what error on the simulator relative to if I had ran it with higher resolution. So they have this really high resolution simulator that's expensive. They run it. They have this really cheap simulator. They run it, and they try to take the cheap simulation, predict the high resolution simulation, and it works really well. So you get like a 86 times speed up by doing this process. So this is a really powerful idea of kind of using deep learning to speed up simulations. So the next thing I want to talk about is chaos. So you might have heard of the butterfly effect. Like a butterfly maybe flaps its wings in Africa, and then a hurricane hits Florida. Like it's like tiny changes in initial conditions can have huge changes on the final result. So if I have some simulation and I change the initial condition by like machine precision, like an infinitely small amount, I can have a massively different result. So this is chaos. Most real-world physical systems actually have this property of chaos. But luckily, in some systems, you can kind of bound the final state of your system within some distribution. So it's not like there's no limit to this chaos. Like if I budge the initial condition a tiny bit, there's actually going to be a range of potential outcomes. So it's not completely random. And luckily for us, that means we can actually use deep learning for these problems. And it's perfect for Bayesian neural networks because you model a range of outcomes. So it's really perfect for Bayesian neural networks because you're modeling a distribution, you're modeling uncertainty of your model. So that's the first key point is kind of if you're working with a chaotic system, you really want to use Bayesian neural networks. Or if you want to know the uncertainty of your model, you should use Bayesian neural networks. So the second key point that I'm going to talk about now is when designing a neural network, you should use existing handcrafted model to kind of influence the architecture. So I'll talk about our research here. So this is the actual problem that we worked on. So I was introducing like chaos and Bayesian neural networks. This is the actual problem that we apply these ideas to. So I work in kind of deep learning applied to astrophysics, and some pure deep learning, but a lot of it's like, I want to solve this problem in astrophysics using deep learning. So this classic like 300-year-old problem is for a system with 3 planets. Like it's called the 3-body problem, but if I have 3 planets around a star, this is an example of a chaotic system. So in this system, if I move a planet by like a centimeter, it can change the time at which it goes unstable by like 1 billion years. So maybe one of the planets will crash into the star if I budge it by like a tiny centimeter, like relative to the system. So this is an example of a chaotic system. So this is very relevant for exoplanet research. So the galaxy is filled with planetary systems. There's like, I think there's like 10,000 observed now. The closest system is actually Alpha Centauri, which is like 4.3 light years away. It's the closest star system. It actually has 2 planets. So one is Earth-sized, which is exciting, and it's in the habitable zone. But basically, the exoplanet research is very quickly moving right now. There's just so many new planets being discovered, and some of the current problems in exoplanet research is the inference methods that you use to figure out what planets are in a system. It's very indirect. So the 2 most common methods are you basically see a dark spot pass in front of a star, and that tells you there's a planet there. The other one is you kind of study the movement of stars, and you infer that like a planet is kind of pulling on it. So they're very indirect, and what that means is you can have large uncertainties on the parameters of your planetary system. So that's one problem in exoplanet research. The other problem is it's very hard to actually simulate the formation of planets, because basically what you're doing is you have all these rocks kind of like colliding and growing into planets over time. It's really expensive to simulate these. So the problem we consider is if we have this given like 3-planet star system, when does it go unstable? So when does maybe a planet crash into the star, or maybe a planet gets ejected from the system and flies off into space? If we can better model this problem, we can better understand planet formation, because maybe we can predict when 2 rocks are going to collide into each other and form a planet. The other thing is maybe we can provide orbital constraints based on the notion that if you observe a given planetary system, it's probably stable because you're observing it. So you can kind of use this instability criterion to constrain parameters of the system. So like this is an example. If you have this blue, yellow, and red planet, and this is like your observed air bars, like they could be anywhere in these regions, like any of these circles, with stability constraints. So like we know if it's going to be unstable, if it's in this setup or not, you can really kind of nail down where the planets are. So our problem, again, we have a 3-planet compact system. We want to find when is it going to go unstable. So we could just like simulate this, like you can just simulate gravitational dynamics. But the problem is planetary systems, we care about how stable they are on like 1 billion orbits. So that's expensive. That's going to take you 10 hours on a CPU core to simulate. But we want to do this really fast. So we want to try to use deep learning to figure out a better relation between a planetary configuration and the instability time. So the general idea is we have this planetary system, 3 planets around a star, and we want to figure out if, like, at 1 billion years, is it going to be stable, or is there going to be a collision? So the trick we use is we kind of generate a time series over the planetary parameters. So like the planets move around, and these are time series because it's the positions of planets over time. We can kind of feed that into a deep neural network and have it predict the instability. So there's kind of like two ways to do this. So one is we can use traditional metrics that planetary dynamics theorists have developed over many years, and kind of use those metrics to predict instability. So this is a paper with my co-author Dan Tamayo. We kind of use these metrics and we predict stable or unstable. And it seems to work well. But the second idea is like, okay, but maybe these theoretically developed metrics don't take into account everything. Like if you give a deep learning system enough data, it should be able to find better metrics. So the second idea is why don't we just feed the raw time series data into a deep learning model and have it predict the instability time, kind of learning the metrics from scratch. So this is what we do. Now, one of the issues is like standard time series models, like Gaussian processes, LSTMs, CNNs, even in scattering networks we tried. We tried many different models, but they all actually have really bad generalization on a validation data set. So we were kind of stuck, like all these standard time series models, they just were not really fitting the system well. So what we ended up doing is kind of using existing metrics and kind of like theoretical approaches to this problem, and structuring our neural network with influence from those theoretical metrics. So I guess like a way of thinking about deep learning in general, it's kind of like loose functional programming. So if you write out a program to do something, like in this example, this is just like some integration method, like you're integrating some function. So if you write out some code to solve some problem, what deep learning basically lets you do is you can replace any part of that program with a neural network. And via auto differentiation, you can kind of find the optimal function for that piece of code. So neural networks, they're kind of like placeholders for functions you don't know. So if you kind of know the rough structure of some algorithm, but you don't know the optimal function at some place in your code, the neural network, it's kind of like a placeholder, and you can learn an optimal function. So like in this, maybe we don't know how to do integration with the trapezoidal method. So we can kind of remove that and then replace that with a neural network. And you get like neural ODEs, and you learn that piece of code with a neural network. So it's really good to think about deep learning this way, because you can tackle many different problems when you think about it like this. So we noticed in kind of trying to develop a model, we noticed that many of the theoretical approaches to this problem are averages and variances of these like instantaneous metrics. So like one metric, maybe it's how far the planets are from each other. So the theoretical metrics would be like the average separation, or the variance in the separation between planets. So that's like the functional version of this. But maybe if instead of just using the theoretical metrics like separation between planets, and you take the average and variance, what if we just learn those metrics and do the same thing and take the means and variances? And so we're basically taking that theoretical approach and just learning an optimal function inside it. So it turns out this works really well. So we can learn a very accurate model with this, even though standard approaches like LSTMs, CNNs, they did not work that well. And so it's kind of like, I don't know, it's so cool that you take the theoretical approach and you learn a piece of it. You take out a piece and you learn an optimal function, and it kind of beats standard machine learning models. I think that's really cool. It's kind of like, it's really important to think about deep learning as like loose functional programming. So we can learn a very accurate model with this. So this is how our model actually looks. So we have this planetary system. We do a short integration to get a time series over the positions of the planets. We then compute metrics for every time step of this system. So we have like positions of the planets at this time step, and we compute the metric. We do that for every time step. So this is like, it's like the theoretical approach, but you're not using the theoretical metrics. You're using the neural network to learn metrics. So the second step, this is motivated by the theoretical approach. Instead of using some CNN pooling scheme, we use a very simple pooling strategy. We take the mean over the time series. We take the variance over the time series. And this is the time series of the learned coordinates. We then pass those means and variances to a second neural network, which is just going to compute the expected instability time. And again, this is a Bayesian neural network. So you want to learn the center and the spread, because it's a chaotic problem. So this is our model, and it works really well, which is like, I don't know, I think that's so cool how like you just structure this deep learning model closer to the method you already know works well, and then you just train the function they don't really know well, and it just works better than like generic deep learning models. I think that's really cool and kind of like such a powerful idea. Like so many models in deep learning, they're kind of close to like the handwritten algorithm, but with just more flexibility in what they learn. So we train on 100,000 simulations and with instability times, and then we try to predict instability times. So these are like the standard, I guess, like analytic approaches to this problem. This is the method with the handwritten metrics, and then this is our method with learned metrics. So we learn the metric and we predict from the metric. So you can see we do better than all of these models. So this is the theoretical limit due to chaos. So predicted on the y-axis, true on the x-axis. So you can see like this spread is because you can never get 100% accuracy on a chaotic system. Like there's always going to be like a spread, and that's just due to chaos. Like you budget by a tiny amount and it'll have a different result. But the fact that this is like a finite width, that just means there's a bound on the chaos. So you can predict it within this spread. So you can see we actually do start to approach this limit, which is cool. So I think in general, when you're doing deep learning on physical systems, it's really important to test the generalization, because deep learning models, they could just be like naively interpolating the training set. Like if you had infinite amount of data, like you could just do k nearest neighbor and like solve any problem if you're not testing generalization. So it's really important to test generalization to see if your model has actually learned something meaningful. So we trained on 3 planet systems. So I think a good test is like 5 planet systems. So like it's a completely different problem. We don't even train on 4 planet systems. Like we only train on 3 planet systems. And to apply our model to 5 planet systems, we basically we cut up the 5 planet system into trios. So it's like the trios. We make a prediction for every trio, and then we kind of aggregate those predictions. So in this case, we care about the trio that goes unstable first. So that's how you can generalize it to 5 planets. So this curve is the log instability time. So this is like 1 billion orbits. This is 10,000 orbits. And so the true result for these simulations is the black curve. And so you can see that our model is the blue curve. And despite not being trained on any 5-planet systems, like it's only trained on 3-planet systems, it can actually predict this curve very well. Like even we were surprised by this. And you can see this is the error bar because it's a Bayesian neural network. And so it predicts this problem really nicely. So this model's learned from scratch, like raw orbital parameters, but it seems like it actually learned something about physics, which is really cool. And so these bumps are due to something called a resonance. And it seems like it actually learned resonance, which is cool. And it beats like analytic approaches. So our model is on GitHub. If you want to try it out, there's training code and like an inference model. So this is more like for an astrophysical audience, but if you're curious, you can try it out. So you can basically generate like a planetary system and then predict when it will go unstable. So it's called SPOC. It is stability of planetary orbit something classifier. I don't know. There is an acronym for it. So it's like to figure out whether planetary systems will like live long and prosper. SPOC. Yeah. Okay, so, and it's a Bayesian neural net, so you can do like proper Bayesian sampling of posteriors, which is really cool. So you can get like a posterior over instability time, like a proper Bayesian posterior. It's fast, which is nice. So yeah, so those are the key points of my talk. So like, if you deal with like chaotic systems, and I think any system or like any problem where you want to deal with uncertainties, and maybe you have natural spread in your data, and you want to model that, you should use a Bayesian neural network. So I really like MultiSWAG, so I recommend that approach. I think Monte Carlo dropout is also a nice approach if you have dropout in your model. And then the second key point is when designing a network, it's important to think about deep learning as like a loose functional programming and structure it close to like maybe a handwritten algorithm to do the same thing, but then just plug in neural networks to the parts you don't really understand. And I think this approach it's a really powerful way to beat like the generic deep learning architectures. So in the future, I think we're interested because we've kind of learned something maybe new about physics. So we're really interested in applying. So I have this other paper like converting models to analytic equations. So I think it'd be really cool to actually convert this model, like the learned metrics, into analytic functions, and we can kind of see like what they are. And then maybe in the future, it'd be cool to learn like a planetary evolution model, because I think we could kind of use the same structure. Yeah. So that's my presentation. I'm happy to take questions.
Awesome. It's really cool how we can incorporate deep learning to learn laws of physics or to incorporate certain domain knowledge and still have it outperform our pre-existing or like classical techniques.
Yeah. I think it's such a powerful way, like kind of thinking about deep learning is like structure it close to your known algorithm and then just let parts of that algorithm be multi-layer perceptrons and learn them. I think it's a good approach. And it results in a more interpretable model too, because you already have this like rough structure. Like in this case, we already know that like these are going to be metrics. So we can kind of interpret these as metrics and compare them to the theoretical metrics.
What I also really like about this approach as well is the fact that it is Bayesian, so you're able to have confidence intervals for each of your values.
Yeah. 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 It's super useful for doing Bayesian analysis of planetary systems too, because you want to work like in science. I remember this prof in undergrad. He said like if there's no error bars, it's not science. So it's really nice to have error bars from a neural network because you can actually do proper Bayesian analysis of systems.
And that would be like its whole other paper or a whole other research project as well. So it opens up so many other doors.
Yeah.
The first question comes from Mushtaba Alam, and they're asking if there are a large number of models with the same loss. I think they're talking with respect to your first initial explanation about Bayesian models. Will that require a very large training or runtime?
Oh yeah, great question. Okay, so MultiSWAG. Well, I guess I'll talk about SWAG first. So SWAG, you don't actually need to train for that much longer. What you do is you just watch the training trajectory. Because when you train, you're going to have different parameters. Like as you approach the optima, your parameters are going to keep changing. So you basically just record the parameters when you're almost done training. You record the parameters over time, and those are like distributions of this posterior of the parameter space. And so another concern is like maybe this is going to be like a huge amount of memory usage. If you record like 100 new models, like 100 new parameters for every single parameter. But so the trick they use in this paper, which is really nice, is you fit a low rank Gaussian. So it's like a Gaussian with basically like few parameters to describe it. So you're actually modeling like the covariance in the parameter space, but you do it with few parameters. So you can choose how many parameters, like how many times the number of parameters to record, so you can control the memory usage. But like definitely if you have like a really big model, I think this approach will fail because you need to like record at least like maybe 10 times the number of parameters. So if you want to control the number of parameters, maybe not. Like maybe Monte Carlo dropout is better because it's a single model with dropout. And then, okay, so the other thing he asked was, or she, was about MultiSWAG. So what you do here is you basically train from different seeds. So every seed, you're going to have a different initial parameters in your neural network, and you're basically going to find different optima when you train the model. You're probably going to find different optima. So it'll just settle into different parts of parameter space, and you repeat SWAG in those modes of parameter space, and then you're going to have like I think we use 30 initial conditions. So we have 30 times the number, like 30 times longer training. But I mean, you don't really need to do like, you don't have to do like hyperparameter search. You kind of do a hyperparameter search on your normal model. And once you've found those best parameters, then you do MultiSWAG for like the final case. And it'll be like maybe 30 times longer training because you need to train 30 more models. But I think that's manageable.
Awesome. The second question is, if each neuron in a Bayesian neural network has two variables, how exactly is gradient descent done? Do weights affect x and sigma equally, or do they each get their own weight?
Oh, okay. So Monte Carlo dropout, like you are modeling every parameter with like every parameter in your neural network is a single number. It's like you're training with dropout, and when you're done training, you just leave on dropout. So you actually haven't changed your model at all. Like you can take any neural network that you train with dropout, you train it, and you just leave dropout on after training. And that'll basically that gives you a Bayesian neural network. You do have to change your loss function. So this is the predicted output of your neural network. These are not parameters for your parameters of your neural network. This is the output. So you're now, for every predicted value, you also predict another number, sigma. and that's like the spread on that value. So like in the example of this case, instead of predicting airline passengers, you would predict mean airline passengers and then spread. Yeah.
Awesome. We also have another question, and it's asking about which languages or libraries allow you to use auto-differentiation to make placeholders out of deep learning.
Oh, so like I think any autodiff library will differentiate through like generic code, right? Like PyTorch, you can write an algorithm in PyTorch with all your normal operations that you would find in like NumPy, and it'll just backprop through them because it uses auto differentiation. So you don't really need like a separate language. Like you just write your algorithm in PyTorch. Of course, you have to use differentiable operations, but in like PyTorch, you can use like for loops and kind of like backprop through the for loop.
Awesome. So I think that is all the questions that we have for today. So with that, I'd like to thank you, Miles, for coming to join us today, and I'd like to thank you, the audience, for joining us today as well. And to see,
Sorry.
No worries.
Okay.
And to see more free content like this, visit AI.SCIENCE and log in to access slides from this and other sessions and many more. Also, make sure you subscribe to our YouTube channel and While Papers Explained to get notified about all the live sessions and other free content we publish.
Thanks a lot for having me.
Thanks for coming.